Let's look at this differential equation where in one set of parentheses I have the quantity square root x plus y plus the square root x minus y. And in my other set of parentheses I have the square root x minus y minus the square root of x plus y times y prime equals 0. And they gave me an initial condition that x is greater than 0. So now here we're going to have to test for homogeneity. But first, in order to do that, I'm going to solve for y prime. So I'm going to isolate y prime on the left. And I'm going to get negative quantity square root x plus y plus the square root x minus y divided by the square root x minus y minus the square root x plus y. Now, in order to test for homogeneity, I need to plug in t's. And if they all simplify and I get back to my original equation, then I know that this differential equation is homogeneous and we can go keep solving this problem. So I'm going to plug in, or I'm going to have y prime equals negative parentheses quantity tx plus ty. See how I plug in that t with the x's and y's plus the square root of tx minus ty divided by the square root tx minus ty minus the square root of tx plus ty. Now from here, I see that I can factor out a root t from each of the terms. So I have negative root t times square root x plus y plus square root x minus y over the square root of t times the square root x minus y minus square root x plus y. Here my square root t's cancel and I'm left back at negative quantity square root x plus y plus second square root x minus y over square root x minus y minus square root x plus y. So here I've done the homogeneity test and I can check mark that it is homogeneous and I can keep going forward with this differential equation. So now here we're going to introduce v's. We're going to say y is equal to vx. And I'm also going to take the derivative of that, so y prime is equal to v prime x plus v. Now I'm going to plug these values into my original equation where I solve for y prime. So on the left, I get y prime x, or v prime x, plus v equals negative square root x plus, I'm going to plug in vx for y, and I'm going to go ahead and distribute that negative, so I'm going to get minus square root x minus vx, again substituting that vx in for y, divided by the square root x minus vx minus square root x plus vx. Now from here, I'm not going to change the problem. I'm just going to multiply by 1. So I'm going to multiply times that the bottom of the term to the top and the bottom. So it's like I'm multiplying by 1. I'm just kind of changing how the problem looks. So I have square root x minus vx minus square root x plus vx over second square root x minus vx minus square root x plus vx. So like I said, that's just multiplying by 1. I didn't change the value of this equation. So from here, I'm going to simplify that right side. And what I get when I simplify is 1 plus v plus 2 square root 1 minus v squared plus 1 minus v over 1 plus v minus 1 minus v. Now in that step I also simplified out all my x's. Since I do have an x in every term, those are eventually going to simplify, so I just went ahead and canceled them all out so that the problem looks a little bit more manageable. So now whenever I clean up that right side, on the top I'm left with 2 plus 2 square root 1 minus v squared over 2v. And again, I can simplify those 2's out, and I'm left with 1 plus square root 1 minus v squared over v. So I'm going to clean that up and set that back equal. So I have v prime x plus v equal to 1 plus the square root 1 minus v squared all over v. So from here, I'm going to subtract that v on the left over to the right. So I have v prime x equals 1 plus the square root 1 minus v squared over v minus v. So from here, I'm going to make that right side all one term. So I have v prime x equal to 1 plus the square root 1 minus v squared minus v squared, since I'm going to have to multiply times v to get the bottom v, over v. I'm also going to change that v prime into dv dx so that it's easy to separate when we get to that point. So I have dv over dx x equals 1 plus the square root of 1 minus v squared over v. Now from here is a variable separable method. I'm going to multiply times v to the left and divide by what's on the top of my fraction on the right. So 1 plus the square root 1 minus v squared minus v squared equals, I'm going to multiply that dx over and divide by x. So I have 1 over x dx on the right. Now from here, I'm going to kind of factor out that left side to make it easier to integrate. So I'm going to get 1 over the square root of 1 minus v squared plus 1 times v over the square root of 1 minus v squared. Now, and that's going to be equal to 1 over x dx. Now, whenever I do FOIL back out that, or distribute back out that bottom, I will get the 1 plus the square root 1 minus v squared minus v squared. So now I'm going to integrate. And I'm going to have to use u substitution in order to integrate that left side. So I'm going to let u equal the square root of 1 minus v squared. When I do the derivative of that, I get du equal to negative 2v over 2 square root 1 minus v squared dv. My 2's are going to cancel in this, so I'm going to be left with negative v over square root 1 minus v squared. From here, I would dv and du. Now I'm going to plug back in to my integral so that I can integrate. So I have the integral of 1 over u plus 1. I'm going to make that negative because of this negative in my du. And then I have du here because this du substitutes back in to this. And then I have the integral of 1 over x dx on the right. So from here I'm going to have the negative ln of u plus 1 equals the natural log of x plus c, where c is an arbitrary constant in this case. Now from here I need to plug back in what I substituted u in for. So let's look back. We have here u is equal to the square root of 1 minus v squared. So I have negative ln square root 1 minus v squared plus 1 is equal to the natural log of x plus c. So now we did that substitution, but we have to look back to where we started. How did we get in terms of v? Well, we set u equal to vx, right, in this step right here. So in order to solve for v, I'm just going to divide by x. So I get y over x equals v. So I'm going to substitute y over x in for v. So I get the negative natural log of the square root 1 minus, like I said, my y over x is v, so y over x squared plus 1 equals the natural log of x plus c, where in this case c is an arbitrary constant. So now that is how you solve this differential equation